This mini lecture is going to look at the idea of what happens when we have an object moving in a circle. How do the forces cause objects to move in a circle? What is that motion related to? How can we analyze it? How can we explore it? So up until now, we've sort of been looking at forces acting in a translational way, in a way that moves something along linearly. What happens if I'm moving something in a circle? So we're going to look at a special case of an object moving in a circle. That special case is called uniform circular motion. And specifically, what does uniform circular motion mean? Well, it's very well named. So uniform meaning constant, circle meaning in a circle, and motion, of course, being motion. So this means that we're moving in a circle at a constant speed. And I'm going to be very careful about saying the word speed. So imagine if we had an object, let's say the eraser. We're not rotating it. We're going to get to that a little bit later. We're actually physically moving this eraser in a circle. So the object itself is moving in a circle. Why might I talk about it as a speed, constant speed? Remember, we had two words to describe how fast something was going, and I'm choosing to use the speed one. Well, let's imagine having that object move in a circle. Let's imagine that we have a ball on a string, and I'm spinning this string around my head, and it's moving in a horizontal circle. If I sort of look at a top-down view of that horizontal circle, so I'm looking from the top down, we see that the ball on the string is moving in a circular path. So here's where I'm holding on to the string. There's the string. There's our ball. And it's moving along in a circle. Now, if I tell you that that ball's moving at 5 meters per second, a speed of 5 meters per second, that means the rate every second the ball travels the equivalent of 5 meters. But what's happening to the ball? Well, it's changing direction. It's curving in a circle. So the ball is changing direction. And since velocity depends on direction, then it must be changing velocity. And this is because of that change in direction. And if it's changing velocity, that means it has to be experiencing an acceleration. And indeed it is. And if it's experiencing acceleration, something's causing that acceleration. And we're going to get to what that looks like. So an object moving in a circle at a constant speed does in fact accelerate. It does in fact accelerate because it's changing direction. So let's explore that acceleration a little bit. Let's look and see what it's related to. This acceleration is related to a couple of things. Let's imagine that we're driving in a car and we're turning the corner of a road. Now, if we were to look at, again, the top-down view of that road, here would be my road, and let's say I'm turning to the right. So there's my turn. It's a pretty sharp turn, 90-degree turn. We can imagine that during a portion of that turn, it's as if we're on a circle. We're traveling along this sort of piece of that circle. So if I'm moving around that curve at a constant speed, then I'm in that uniform circular motion for a portion of that trip. Now, let's imagine that we're moving along and see if we can come up with some of what this acceleration is related to. You're in the country roads of Wisconsin and you're going beautiful curvy country roads. How do you feel when you go around really tight curves versus really gradual curves? Well, it's a lot harder to keep your car. It takes more force. It takes more work to turn, more force to turn around those tight curves, if we think about it in terms of a force. So if I decrease the radius, I make those curves tighter, the amount of force it takes me and everything else that's causing that force to turn around that corner goes up. So if I decrease my radius, I increase the force needed. Mass hasn't changed, which means I must have increased my acceleration. That acceleration had to have gone up. All right. Well, what else makes it harder to turn around that corner? When we hit a corner, we tend to slow down, right? So if I'm going too fast, it also is harder to make that corner. So if I increase my speed, and I'm going to use v, it's not the vector of velocity, but just the speed, then I increase the force needed, the net force, which means I'm increasing my acceleration. And it turns out that that speed has a lot bigger impact on that acceleration than the radius does, or what's needed to cause that acceleration. So the relationship for that acceleration is actually the magnitude of it, and we'll get to the direction in a minute. So the magnitude of that acceleration is actually equal to v squared, really influenced by the speed over the radius. All right, so the acceleration to get this object moving in a circle, to change its direction, is related to the speed squared and the radius. Now, what about the direction of that acceleration? Remember, acceleration has direction. This is just the magnitude. It's just the value, the amount. What about the direction? Well, let's look at this direction for just a moment. Here we have a ball going in a circle. Now, if we think about the direction that the ball is moving at this point, we know that this is the object's velocity at that point, perpendicular to the circle. If the ball was at this location, we know that the velocity of the ball is, again, perpendicular to that surface. At this point in time, the ball is moving straight up. At this point in time, the ball is moving to the right. Well, let's look at 2 points in time very close to one another. So, if I have the ball at this point in time, we know that the velocity is pointing at this location. So I am taking my velocity vector, and it's being changed in this fashion as we go through the rotation. Now I want us to think about what's causing that change in this example to help us give an idea of direction, and then we'll see if the vector algebra works. They should be consistent, of course. Let's imagine that it's only the ball moving on the string. So the only interactions happening with this ball is the string. So the string is the only thing interacting with the ball, the only thing causing a force. It's the only thing that's changing that object's direction. If the ball is at this location in space, is the string pulling the ball this way or pulling the ball that way, pushing the ball that way? Well, if you imagine as we're spinning that ball around in a circle, it's sort of pulling the ball in this direction. So there's a force, and in this case it's by the string, because that's the only interaction that's happening, pulling the ball in that direction. Now when the ball's at the top of our picture, so when it's like forward in front of me, is the string pulling the ball this way or pushing the ball that way? Well, it's pulling the ball in this direction. So the force of the string, I'll give that a little tension, the force T, is pulling the ball in this picture, that direction. Now if I had the ball here, so again the ball's moving in this circle, how would this string be exerting a force? How would this string be causing that acceleration? Well, again, pulling, excuse me, again, pulling the ball in this direction. Now, how are all of these related? Well, they're all, and this is to the left, this is down, that's sort of up and to the right, based on my picture. But they are all related, and they're all towards the center. Every one one of them. And if I put the ball anywhere on the circle, they're all towards the center. So the direction of this acceleration is a little bit differently thought about. We can think of the direction of this acceleration as towards the center. And when we're analyzing forces, and we'll do this as an example, when we're analyzing forces, we have to figure out what towards the center means for our given situation. And we have to actively put that direction in because towards the center means something different depending on my circle. So we'll be very explicit about putting in the direction of that acceleration so that we are always towards the center. We'll be very explicit about putting in the direction of the net force that causes this acceleration and making sure it's towards the center. Because, of course, every acceleration is caused by a net force, or the sum of all the forces acting in that direction. So does that work from our vector analysis standpoint? Let's imagine that I have two vectors. We'll call this vector initial and final. So let's not do initial and final. We used that already. We'll do it in 2 points in time, 1 and 2. So let's imagine I have vector 1 and I have vector 2. Oh, here's 1 and here's 2 slightly at an angle. If I were going to add those two vectors together, or in the case of a change in acceleration, we know change in acceleration, a change in velocity. I want to look at how this velocity from 1 to 2 changes. My change in velocity is my second velocity, v2, minus v1. Over time, that's acceleration. So that's really as if I'm saying v2 plus a minus v1, because I like to add vectors. So I need to turn vector 1 around. So this is minus v1, okay? And then I take v1 and I put it on to v2, and there it is. And the resultant vector is right there. So if I look at this resultant vector and I put it up here at the location of v1 where I'm changing it between here, what direction do we see? It's towards the center. So we can do that at any point in the circle, and we'll see that the change vector, which is related to my acceleration from a definitional standpoint, right? The acceleration is the change in velocity, is indeed towards the center. Now, this acceleration does have a name that we associate with it. You'll hear, and it's very related to the towards the center idea. This is called our centripetal acceleration. And centripetal acceleration means center seeking. So, centripetal means center seeking. So we can remember the direction of that acceleration to turn an object in the circle, the acceleration an object experiences when it goes in a circle, as our center seeking. And the forces, whatever forces are causing that object to move in a circle, are causing that centripetal acceleration. So just like we've talked about before, it's the net force that causes the acceleration. It's the sum of all the forces acting in the direction of towards the center that cause the centripetal acceleration. Okay. So when we analyze objects moving in a circle, we are going to apply Newton's second law. We are going to put in, if it's moving in a circle, in one of our directions, instead of just ma, Newton's second law, we're going to put ma sub c. So we're going to look at the circular acceleration, the acceleration of moving in a circle, and then we're going to have to be very intentional about that direction when we replace that acceleration with its magnitude relationship. Now, I want to bring up one more little thing that you hear about when you think, or you've heard before when you think about objects moving in a circle. And you hear this other word often. And that other word is centrifugal or centrifugal. And I want to address it because it's something we hear and something we experience. So I want to make sure that we are at least recognizing that this is used to describe something and how it relates to how we're going to analyze things. So what is this centrifugal. And we often hear about it as like a centrifugal force. Now, it has to do with relative motion, and we're not going to address that in this class, but what does it mean in common language, and how have you heard it before? Well, imagine you're on one of those nauseating amusement park rides where you're sitting in a swing and you're starting to go around in a circle. You're experiencing circular motion, and you feel like you're getting pulled out, pulled out, pulled out, pulled out. And even once those swing holders, the chains, are at their maximum they're going to be, and we might analyze something that looks like that, you still feel like you're being pushed outwards. But if we looked at the analysis of the interactions of the forces, there's no interaction that's in that direction. The only interaction that's happening is similar to the one that we represent here. It's the forces towards the center to get it to move in a circle, or it wouldn't turn. So why do we feel a force? It's just a feeling. That's all we're feeling. And it actually has to do with our physiology and our brain's interpretation of the signals it gets. So inside your head, inside your ears, is your balance system. And there are these tiny little hair cells with tiny little rocks on them, calcium deposits. And when we tilt our head, those tiny little rocks fall down due to gravity, causing the hair cells that they're sitting on to bend. And when those hair cells bend, the brain gets a signal that your head is tilted or that you've been shifted. Something has changed about your motion, and you interpret that as a force, as an end, because you've been accelerated. Well, now imagine that you're on this little bitty ride. And as you're on this ride, let's imagine this string is our ride and we're the ball, okay? So the ball velocity is in this direction. And the string is pulling the ball around the corner. The string is causing that acceleration to turn. The acceleration is the turning. It causes the velocity to turn. So your little tiny hair cells are slightly disconnected from the string. And so they continue a little bit straighter, and the rest of your body turns, which causes those hair cells to bend, which causes your brain to get a signal. That signal to the brain is no different than the signal if I shoved you a little bit in that direction. So your brain's just a little confused about the signal it's getting, not because there's something pushing you out, but because of Newton's first law that you're just going to normally go straight. And so those little rocks go straight a little bit at a different turning than the rest of your body. So you get a signal. But this doesn't exist in our relationships, right? So we are going to not utilize that. There is no outward force. The only forces acting on the object to turn it into the circle, turn it in a circular motion, are forces that are working together that are towards the center. All right, so that's the idea of uniform circular motion. That's the idea of the acceleration that the object is experiencing, what it's related to, and we call it the centripetal acceleration. The direction is towards the center, and it's caused by, as we'll see in the next example, the forces that are all in that direction, just like Newton's second law for any forces. All right, good job.